Okay. So can you see the screen? Yes?
Yes.
Good. So, hold on guys. It's really odd. Okay, it's much better. Okay, so we started the first order system and I applied a impulse as the input to the system and B as the unit step as the system. So you're gonna tell me, Payman, what is the unit step? Is that as we discussed the robotic systems, okay? So this is a 2D of freedom robot that you pass in ME532, that's right? And you want to move this to pi over 4 means 45 degree, and this link to pi over 6, okay, or 30 degree, say. So on the other hand, you want to push this robot to this pi over 4, and you want to push this link or this link of the robot to pi over 3. So you have two steps input to the system that you want to follow. See what I'm saying? And at the end of this course, I'm going to develop the MATLAB code and PID code in the ODE format that I'm going to do this. See what I'm saying?
This is question.
Yeah. Yeah, exactly. This is, yeah, exactly. This is 2, if you pass ME532, is 2 degree of freedom system. You have one actuator here and one actuator here. And the angles theta 1 and the theta 2, okay, is it recording? Yeah, okay. So theta 1 and theta 2, they are independent. You know what I mean? You can keep this constant and move this and vice versa. See what I'm saying? The number of independent coordinates of the system is called a degree of freedom. So I hope that you learned this from the robotic course. Okay? So, but for the first order system, we examined this in the MATLAB coding and the Simulink, and the system that we were considering was spring and the damper, right? So F, KF, KC, and we saw that the output X over F, X means this displacement, was 1 over tau S plus 1, and we named tau as the time constant. So I'm not going to the RC circuit and the tangle to water example because these are the things that I'm teaching in ME430. You have to know this before coming this course. So these are also the first order systems, okay? I'm just sticking to this example. So see if that your input to the system is a ramp. So if it is a ramp and you apply the Laplace transform on the both sides, you get the input to the system as 1 over s squared, as you know from the table I provided for the Laplace transform. So implementing this here, so x gonna be 1 over s squared 1 over tau s plus 1, obviously in the frequency domain. So you can decompose this as a over s squared plus b over s plus c over tau s plus 1, because it has two poles at the origin. See here. After this, we are naming the roots of the denominator as the poles and the roots of the numerator as zeros. So imaginary real axis, it has two poles at the origin. So you have to decompose it like this, s squared s. If you don't do that, you made a mistake. So the simplest and trivial way is you say S square tau S plus 1 gonna be A tau S plus 1 plus BS tau S plus 1 plus CS square. And obviously this equals to how much? Equals to how much? 1. So if you write that, you're gonna have and sort it based on the S order. So you're gonna have A tau, see A tau plus B tau S square let me see. No, there's no A here, guys. So gonna be, sorry guys, because I'm developing with you, I have no notes. So B tau S square plus C in S square plus A tau plus B in S plus A equals to 1. This means 0 S square plus 0 S. So this is 0, this is 0, and A is equal to 1. Having A equal to 1, you can use this here, A tau plus B equal to 0. Just put it here, you get B as minus tau. Then you put it here, B tau plus C equal to 0. You put here, you get C is equal to tau squared. You got it? Yes? So now you have X equals to, in frequency domain, is 1 over S squared minus tau over S plus tau squared in tau S plus 1. If you want to go back to the time, what I have to do? Come on. What I have to do if I want to go back to time from frequency? Yes, here we go. So X of t gonna be inverse of this, I just told you, is, see, is ramp input minus inverse of this is step input. That's right. Step input minus tau, step is 1, unit step. And then you can write this as this. I'm taking this out. You can write as tau S plus 1 over tau. You can factor out tau in the denominator and remove one of the tau's in the numerator. So which function gives you such a transfer function? Now you know it. Yes, it's tau e minus t over tau. And let me delete this. And this is your response when the input to the first order system, which is stable because its pole is in the left hand side. Look at here. The poles of this system, as I told you, is here on the left hand side. One pole, 1 minus tau. Stable system is like this. Can I go to next page? Yes. So x of t that we got was t minus tau plus tau e minus t over tau. So if I want to plot it, here we go. T versus x. At t0, x of 0 gonna be, this is 1, so gonna be 0 minus tau plus tau. So gonna be 0. Here we go. At t infinity, as we did in the previous cases, x at the large number, so this gonna be goes to 0. You're gonna have t minus tau, right? And remember that in the unity feedback block diagram, plus minus, and here is the open loop transfer function, 1 over tau s always, as we did in the Simulink. So, and output is this, input is f. I'm showing you the time, but you have to show in the frequency. I'm just showing for the teaching purposes. So you say x minus tau, f minus x. So what I'm going to do, I'm going to say t minus x is equal to tau. See, t minus x is equal to tau. So you tell me what's the name of this signal in the control? What's the name? Yes, error signal, E. So it says that you have a constant error signal. So ESS, you have a steady state error signal, which is tau, constant number. And we know the name of this is time constant we defined for the first order system. Time constant. You have a steady state error signal. So if this is your input to the system, see, this is T. See, T. Here is 45 degree. Sorry. Input to the system. So the output, it says, if I rewrite this here, let me show that to you guys. It says x at infinity minus t, or input to the system, is minus tau. Means x is tau lower than that. So you're gonna have this. It comes a transient response and then constant line. Here is a constant line. Here's a transient response. See? As mathematics shows here. Clear, everybody? So on the other hand, the difference between them here is how much? Is how much? Tau. Here is tau. Here is tau. Because this is constant, right? So you have a steady state error signal. So system is stable. But has steady state error. Solution? I'm going to teach you eventually. I controller. I controller function is to remove steady state error signal. Here we go. Any system that has steady state error signal has I controller. So if you apply here, what is I controller? You tell me. I told you. Yes, means Ki over S. That's right. Ki over s. If you apply this controller here, I'm going to show you by coding eventually in math. You must have this. We're going to examine later on March, April. Okay, you're going to have this. You're going to go like this. See? So I controller function is to remove steady state error signal. See what I'm saying? Yes, everybody?
I think so.
So, and its mathematical proof is here. So ESS, based on the final value theorem, is limit S input to the system f of s 1 plus g open loop transfer function. This limit of s input is ramp, so it's 1 over s square 1 plus 1 over tau s open loop transfer function. Open loop, okay? Open loop transfer function 1 over tau s. Guess what this goes? So it is limit of 1 over s plus 1 over tau if you move the 1 over s to the denominator when s goes to 0. Is to 0, tau. There we go. So can I go to the next page? Yes? Can I? Good. So saying that, the take-home message that for systems with steady state error signal, error, unit I controller. So before going to Simulink and MATLAB, I have to again rephrase this because in MATLAB we have step function, okay, in coding, but we don't have ramp like in Pulse. So what I'm gonna do, I'm gonna reformat the transfer closed loop transfer function. X over f is 1 over tau s plus 1. So the input to the system is ramp, so it's 1 over 1 square. It's equal to 1 over tau s plus 1. But I can write this as 1 over s multiplied by 1 over s. What is this? You just told me. Step. Because we have a step command in coding, that's right. So x over step, again, input to the system. I'm moving this 1 over s here. Gonna be s squared tau plus s. You see, for plotting in the MATLAB coding, by coding, I change this transfer function to this transfer function from first order system to second order system. But input is a step. So having that, you have the numerator gonna be, because it's second order system, see, then MATLAB coding, gonna be tau 1 0. There's no constant number here. There's no constant number 0. Here you have 1 0 0 because there's no s squared, there's no s. See what I'm saying? Yeah, simplify now. Reformatting the transfer function to be compatible with MATLAB step commands. Okay? What do you mean by simplifying? What do you mean? Yes, 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 yes. I'm saying reformatting, reshaping transfer function. Okay, not simplifying. Okay. Yeah, yeah. So for example, I'm saying tau is time constant of the uh, spring and damper is 2. Just putting 2 number here. Okay. But let me go to MATLAB and then I continue for the parabolic input. Okay. Um, and let me. Okay. So what I'm gonna do, I'm gonna say, okay, your num is 0, 0, and 1, and then it's 2, 1, and 0. Okay. Then I'm gonna say figure 1 step because we changed to step. Num and then. Okay. For time of 20 seconds from here to 20 seconds, and here is time. Then I'm gonna plot the input to the system. So plot time, and the input system is, let's say, input is t, is y over t, that's right, input to the system. Time and in, and red, and grid, and title, ramp, response. So I'm gonna save this in M530 ramp and parabolic, because today I'm gonna do that parabolic response. Okay. So having this, if I run this, you have to see what I plotted by hand. Here we go. You see that we have a transient response here, and then a steady state response here. So if you zoom in, here, you see that here's exactly is 2. Here's exactly 2. Here's 2. 2. Constant error signal. See what I'm saying? Even if that you can, let me put this command. When you put say close all, when you run code, it's gonna close all the figures, and the clear means clear the screen, working space. I mean. So I'm gonna put also another to tell you this to then 1. I'm gonna increase the time constant to, I don't know, 6. If I do that, guys, when I increase the time constant to 6, I'm increasing what? You tell me. Look at here, guys.
Square.
Yes, I'm increasing the steady state error signal. So you're gonna see more deflection from here like this. See what I'm saying? So if I plot this, so see then, and I'm gonna say hold on step, and then 1, and then hold on. See, if I run this, here we go. See the error signal increasing. See, steady state, and here is gonna be 6, I bet. Let me show you. See, here is gonna be 6. Obviously it is. Look at here, 6. Understand? Yes. So, because I'm sharing with you, let me put a legend. It is tau equals to 2, and the other was input to the system, input, which is what I say ramp, and tau equal to 6. There we go. Okay, if I run this, here we go. Okay. So the red line is ramp. This is tau 2, this is tau 6. Understand, everyone? So now going to Simulink. Let me go to Simulink. I'm going to share the files with you, no worries. Going to Simulink. Okay, what I'm gonna do, go on. I'm just gonna copy all of these, put in the new file to save it as ramp. Okay, I'm gonna save it as ME530 as ramp response. Okay, first of all, we don't need to change the transfer function because here is open loop transfer function. So double click on this. So it's a first order system. We're gonna say 0 and 1, and here is 1 over tau s. Your tau is 2 tau s. Here we go. Understand, everyone? Yes? Look at here. 1 over tau is open loop transfer function. Don't forget, I'm again emphasizing, in MATLAB coding, you put closed loop transfer function, even reshaped transfer function, but when it comes to Simulink, for the linear systems, you have to put the open loop transfer function. Okay, but despite impulse, we have ramp command in Simulink. See, just move it here. Here we go. So instead of this, just put here. There we go. Just double click on that. So slope is 1, means 45 degree. Start time 0. Always check this. And then save. So if I run this, so let me change first to 15 seconds. And run it. So you see that this is exactly what we plotted it by coding. There we go. This is the ramp, transient response, and steady state response. And here is exactly 2. See, 10, 8. say 12, 10, 14, 12. So exactly this. So going here, I just wanna copy and paste this to make a comparison. Now I'm increasing the time constant to plot the error signal, guys, to 6 as we did. 1 over 6s. Here we go, round. First of all, I'm gonna increase the number of the inputs to the max as 3. Then I'm gonna put this here. I don't need this, but I want to plot the error signal. Right click. Oh no, I need a max. Okay, here we go. Okay, here we go. These are the error signals, huh? We got it. So, and I don't need these also because here we go. Okay. Oh, what's this? Okay. So if I increase this to 30 seconds and I will run it, you see that this is what exactly I plotted. See, 10, here is 4. Okay, so this is like that, and this is the error signal, guys. One of them goes to 6 eventually. This is 2. 1, 2, 3, 4, 5, 6. Error signal is constant. To make it more visible about the constant, because I'm sharing with you, I'm saying 40 seconds. Here we go. See, goes to the constant 6 error signal. So you need the eye controller to make this error signal to 0. On the other hand, when you add the eye controller, the rest is gonna behave like this. Look at here, my hand. It's gonna go to 0. The same for this. It's gonna come until here and then goes to 0. Clear, guys? Yes? Good. So I will send this by Canvas to you. Let me close this. And, okay, let's continue the course. So after doing that, okay, I want to move to the next page. Okay. So now D, if the input to the system f of t is parabolic, okay? So you know that from the Laplace transform I taught you, you mean that f of s is 1 over s cubed. So x over f for first order system, for any first order system that is in this format, stable. RC circuit that you learned in ME430, or tank of the water, or the massive spring that I'm teaching you as an example. Okay, so it's gonna be x gonna be 1 over s cubed 1 over tau s plus 1. Now you know it, you have to write as this: a over s cubed plus b over s squared plus C over S. You are not allowed to write only this because it has 3 poles at the origin. You cannot eliminate the poles. Okay, 1 over tau S and D. There we go. Good, guys. So you can write this as this. A in tau S plus 1 plus BS tau S plus 1 plus CS square tau S plus 1 plus DS cube over S cube tau S plus 1. See, the highest order is 3. So you can say, and reordering, S cube D plus C tau here, that's it, plus S square C from here plus B tau plus S gonna be B plus A tau plus A equals to how much? Again, 1. Let me rewrite this. D plus C tau. Let me double check because I'm looping with you. C tau S square gonna be C plus B tau plus B plus 8. Okay. So obviously you see from here that the A is equal to 1. A equal to 1. If you put it here, you get B equals to minus tau. If you put it here, you get C is equal to tau square. If you put it here, you get D is equal to minus tau cube. Bingo. Everybody agree? Good. So on the other hand, your X gonna be 1 over S cube minus tau over S square plus tau square over S minus tau cube tau S plus 1. I'm gonna back to time domain. What I have to do, you tell me now. What I have to do? Yes. So X of t gonna be, what is this? Come on, look at here. Yes, 1 over t tau square, t square. What is this from previous one? Yes, minus tau t. Yes, go ahead. Any question? Okay. What is this from the previous class? Step, that's right, unit step, tau square. Now again you can write this as this, tau square S plus 1 over tau. So this is gonna be plus tau square E minus T over tau. Guys, you know that this is decaying term. That's right, I taught you, yes? This is decaying term. What does it mean? You tell me physically. When time goes to infinity, this goes to how much? 0. So this is decaying term with vanishing term. So what is this, guys? Based on control class, I'm teaching you. Based on this. Decaying, growing? No. Listen to me. What is this in the control class? What is this? What's the name of this? What's the name of this? Yeah, X is? What is closed loop transfer function? Look at your notes. I want that you tell me. I know the answer. Okay, what is here? Name this. What is here? Output here. That's right. Here is input. So your F is input. F is input. So this is what? This is what? Input. This is what? Output. So you're saying, I'm saying you, I'm telling you, so 1 over t, half of t squared minus x of t equals to, I'm moving these to other side, t tau t minus tau squared. So what's the name of this in the block diagram? You tell me. Error signal, exactly. So this is E. So your E here changing with time means your E increasing is not constant anymore, like as the ramp input. So when time increases, E increases. See what I'm saying? So when time goes to infinity, E goes to where? E goes to where? Infinity. Oops. Now your system is in trouble. Not even your error signal is constant, but it goes to infinity. So you need a strong I controller to make it 0. See what I'm saying? Yes? Yes? So, mathematical proof of, oh, can I go to the next page?
Yes.
So, mathematical proof of this is again steady state error signal. The limit of S, f of S input to the system, 1 plus G open loop when S goes to 0. The limit of S is parabolic is 1 over S cubed, 1 plus 1 over tau S when S goes to 0. So it's the limit of 1 over S squared plus S over tau when S goes to 0. What is 1 over 0? Infinity. A large number. See what I'm saying? So if I want to plot this here, I mean, what we plotted. So if this time, if this x, so let me say this is input to the system, parabolic. This is f. So based on whatever we derive together using Laplace transform, the system starts from here and time increases. So you see the error signal, what? Increasing with time. These are error signals, each of these. See what I'm saying?
Yes.
So don't forget that in the ramp, it was constant, like this. In step, it was 0 error signal. In impulse, it was 0 error signal. But in the parabolic, you have a big problem to solve. So before going to the MATLAB and simulating the next class and plot this, now I'm going to make a table for summarizing what I taught you about the first order system. Here is ESS, here is impulse, unit step, ramp, and parabolic. You can easily say error signal is 0, 0, tau, and infinity. So you see that after this point, your first order system needs what? Controller. To make error signal to 0. This is summarizing of the typical first order systems with x over y, output over input is 1 over tau s plus 1. Now I have a stupid but funny question from you. Why I don't write like this, guys? You're gonna tell me, okay, tau is minus 1. This is the first order system. Do we need to even judge this? Do we need? No. Your first part no is what was right, but the second part was not right. What's the pole of this system? Pole of this system is 1 over tau. So here, what's the pole of this system? What? You can't solve this equation? What? You can't solve this equation? You can't solve this equation? So yes, yes, here, yes, means that your system is unstable. This system is unstable because in the right hand side. But this system is stable because in the right side. Your system is unstable. I don't care about the error signal. First you have to fix it. See what I'm saying? You know why the system is unstable? You know why it is? Look at here, guys. Everything is trivial mathematics. I can write this like this. 1 over tau s minus 1 over tau. Which function Laplace transform is this? You tell me. Exponential. So suppose for your input to the system is impulse, so gonna be 1. So the output gonna be x gonna be 1 over tau e plus t over tau. No, because here is minus, is gonna be plus. So when time increases, x gonna increase. So it's gonna be like this, guys. This is the input to the system, impulse. Look at here, and this is the output of the system, guys. Wow. You want to follow this, but it goes up. Your system is unstable. See what I'm saying? Yes? So that's why when your poles are located at the right hand side, your system is unstable, and located at the left hand side, your system is stable. Or let me put with the green being okay. Stable. And I taught you when the poles on the imaginary axis What's the name of that? What's the name of that? Yes, oscillating forever. Marginally stable. Like as the pendulum problem. That's why we don't care about this to analyze like this, because system is unstable. We are caring about the stable first order systems. Yes, we're gonna fix the control the unstable systems, but when the system is unstable, we don't care about the error signal because system gonna behave crazy by itself. We're gonna fix it. We want to judge about the stable system about the error signal first. Okay. Obviously, we have to do that. When I teach you the Roth stability criteria, I'm going to teach you how to judge the system is stable or unstable. Okay. So I'm done for this class, and we're going to go to MATLAB Simulink for the parabolic. Then I'm going to go to body plot or the frequency response, which is very important. Okay. Then we're going to go to second order systems.